Hello again. Today we're talking about Pushdown Automata or PDA. These machines are more powerful than DFA and NFA and help us recognize context-free languages. Let's get started. A pushdown automaton is like a finite automaton with an extra tool, a stack. Think of a stack as a pile of plates where you can only add or remove from the top. PDAs are commonly used in programming language compilers to check syntax. For example, they can ensure parentheses are properly matched in code. Unlike finite automata, PDAs can store and retrieve symbols, making them ideal for recognizing patterns that require memory, such as nested structures. There are two main ways a PDA accepts input by reaching a final state or by emptying its stack. A PDA is defined as a seven-tuple finite set of states, input alphabet, stack alphabet, transition function, initial state, stack bottom symbol, set of final states. The stack allows the PDA to push symbols onto it, pop symbols off, or do nothing. The stack memory is what distinguishes PDAs from DFAs and NFAs. Let's design a PDA that accepts strings with equal numbers of A's and B's over the alphabet. When the PDA reads an A, it pushes it onto the stack. When it reads a B, it pops an A from the stack. If the stack is empty after reading the entire input, the string is accepted. For example, the string ABBBAA is processed as follows: push 3 A's, pop 3 for the B's, and then push one more A. The PDA halts in the final state if the stack is empty. PDAs play a critical role in programming language design. They're used in parsing to check syntax, ensuring that code adheres to the rules of a language. For example, they validate nested structures like parentheses and the mathematical expressions or HTML tags. DFA versus PDA. DFA has no memory, meaning it cannot handle nested or recursive structures, while PDA has a stack memory, allowing it to recognize context-free languages like balanced parentheses or palindromes. PDAs use stack operations to track the structure of the input. Push adds symbols to the stack. Pop removes symbols from the stack. This last in, first out behavior makes PDAs capable of handling patterns regular automata cannot. Another PDA example, strings with nested parentheses, such as open open, close, open, close close. Push an opening parenthesis onto the stack for each closing parenthesis. If the stack is empty at the end, the string is accepted. Can PDA recognize all languages? No. PDAs are limited to context-free languages and cannot recognize context-sensitive or recursively enumerable languages. Why is PDA important? Because it bridges the gap between simple automata and more complex computational models like Turing machines. While PDAs are more powerful than finite automata, they cannot handle languages requiring more complex memory structures, such as context-sensitive languages. For example, PDAs cannot recognize patterns like A and B and CN, which require three-way comparisons. Common PDA challenges. PDAs can sometimes struggle with ambiguous grammars. Ambiguities occur when there are multiple valid ways to parse a string. This can complicate their design and transition functions. You might be wondering why PDAs are limited to context-free languages and cannot handle more complex patterns like A and B and CN. The reason lies in the stack's inability to store and compare multiple pieces of information simultaneously. For example, recognizing A and B and CN would require two separate stacks to count and compare the three groups of symbols. Another interesting property of PDAs is their ability to operate deterministically or non-deterministically. Deterministic pushdown automata (DPDA) are less powerful and can only recognize deterministic context-free languages (DCFLs). Non-deterministic pushdown automata (NPDA) can recognize all context-free languages, making them more versatile. And finally, PDAs are the backbone of parsers in programming language compilers. They ensure that code follows proper syntax, which is essential for creating error-free programs. Without PDAs, it would be nearly impossible to efficiently parse and validate complex nested structures in source code. And that is the pushdown automata. In this video, we explored how PDAs work, their formal definitions, and their applications in recognizing context-free languages. We also looked at examples to see them in action like balancing parentheses and matching equal numbers of A's and B's. I hope this video deepen your understanding of these computational models. Uh, in the next video, we'll tackle Turing machines, the most powerful computational model yet. We'll dive into their mechanics, examples, and why they're considered the foundation of modern computing. You won't want to miss it. See you there.